Aren't you recording? Good day, and welcome to Africa Teen Geek Online School. This is the STEM Digital School, and if you have just joined us in here, this is the grade 12 Physical Sciences classroom. It's grade 12 Physical Sciences, okay? Today is the 17th of July 2020, and yes, we've been on the Doppler effect. We've been doing some revision on the Doppler effect. So I hope that everybody is following through the work and is getting to understand everything that we're doing for term 3. Okay, so just a recap, we did the Doppler effect on sound, on light, on galaxies. We did it on all the different types, the sonograph, Dopplers, and I hope that you know the different types, how they operate, and the different ways in which they are operated. Okay, writing you again that I'm working on the Siavula textbook. If you do have it, please make sure that you go through it. And if you don't, whatever CAPS approved textbook that you have, that is good with me. You can be able to work through it. And also reminding you that if you need some more textbook, because since you guys are in matric and there's a lot of question papers that you guys are working on, and different viewpoints, and I know that you guys are constantly studying, constantly on your books. Please, you can download Snaplify and get some more textbook for absolutely free until the 31st of December, which by then hopefully your exams would have been uh, passed. It will be past your exams already. So guys, I encourage you guys to keep studying and practice is the only way that you guys are going to pass. But make sure that you practice with understanding. Okay, don't just write problems you don't understand. Just make sure that you understand, and that's why you have me here in this classroom to help you do that. Reminding you guys as well that you can send a chat whenever you're getting stuck. Okay, so don't get stuck alone, don't stress alone. Nonkululeko Matondo, and I am the grade 12 physical sciences teacher. Running the term through work that we're doing, we did work, energy, and power, and it's a Doppler effect. Those two modules are the ones that we're doing for term 3. Okay, so we're going to be doing some exercise of the Doppler effect. Remember, we started yesterday, we did a lot of sound problems, and then today we're going on further. Okay, so it says here, okay, we start on number 6.2. It says, write the definition of each of the following terms, right? The Doppler effect, the redshift, and the ultrasound. Okay, so what do we know about the Doppler effect? We know that the Doppler effect occurs when a source of waves and or an observer moves relative to each other, okay, resulting in the observer measuring a different frequency of waves than the frequency at which the source is emitting. Okay, I hope that makes sense to you guys. So basically, the sources the source's frequency remains the same because the source is not moving away from the sound. The sound is what the source is carrying. So there's going to be a different frequency of the observer, who will either be getting closer to the sound or getting farther away from the sound, which will have a change in frequency, the change in pitch. Okay, I hope that that makes sense to you guys all. So let's see what is the rate shift. The rate shift is the shift in the position of spectral lines to longer wavelengths due to the relative motion of a source away from an shift. So it's a shift in the position of spectral lines to longer wavelengths due to relative motion of the source away from the observer. So now we are talking about Now we are talking about light. Okay, remember what we said about light is that you are farther away from the source, and that will be your much redder light, light spectrums. Okay, and the closer it is to the sound, the shorter the wavelengths are, and that is your blue shift. Okay, please make sure you remember all these things. Okay, so the ultrasound or ultrasonic waves are sound waves with a frequency greater than 20,000 hertz. So that is super, super loud. That's things that the human ear cannot begin to comprehend. But um, because we're doing physics, these are the sounds that we these are the sound frequencies that we have. Okay. Okay. So moving on, it says on number 2, the hooter of an approaching taxi has a frequency of 500 hertz, right? So the hooter of an approaching taxi has a frequency of 500 hertz. As you know, taxis are always hooting. So that's why this is a good example. Okay. So as you know, the taxis are always hooting. So that's why this is a good example. So you can be able to imagine the hooter from wherever from the point where the taxi appears from the corner up until the taxi gets to you, and from that point when it passes away from you. So those there's a change in frequency in both scenarios. Okay, so there is a change in both scenarios. So if the taxi is traveling at 30 meters per second and the speed of sound is 340 meters per second, calculate the frequency of sound that you hear when the taxi is approaching you. Okay, so here we're looking for the frequency of sound that you will be hearing. So you're the person standing and the taxi is approaching you, and the hooter is on non-stop. So when you are standing, what does that mean, guys? That means that your velocity will be equals to zero because you are not moving. You are waiting. You are standing. So you're waiting for your taxi to Pretoria. But what approaches you is a taxi to Johannesburg. So you will not stop the taxi, but you can hear the sound of the hooter that's approaching you, right? So if the taxi is traveling at 30 minutes, the taxi is approaching you. Okay. So when the taxi is approaching you, it means that the source is moving towards the observer. And what do we know about that? We know that the velocity of the source will be a negative. Remember our little block diagram that shows that when a source is approaching the observer, the velocity becomes negative. But when it's moving away from the observer, then the velocity is a positive. Okay, so remember those are the two things that are likely to change in this case. So it's going to be the frequency of the listener in open bracket, the velocity, the speed of sound divided by, why is it we only have the speed of sound? What happened to the speed of the listener? The speed of the listener is equals to zero, so it doesn't count in this equation. Okay, so it's going to be v over the v minus 30, which is what has been given to us as the velocity of the source. And that all of that will be times by 500 because this is the frequency of the hooter. Okay, so this is what the frequency of the listener. Basically, this is what the frequency of sound that the listener will be hearing will be 548.4 hertz. Okay, so now they say when the taxi passes you and is driving away. So the only thing that's going to change in this case is the sign of the speed of the source. It's going to be now a positive. You see, so now the taxi is moving away from the observer. The only thing that changes is the speed of the observer. I mean the speed of the source, the sign. It becomes a positive. Nothing else changes, guys. So it's going to be 340 divided by 340 plus 30 and times it by the 500 that was given to us, and that will be 459.5. But this makes sense, guys, doesn't it? If you look at these two answers, this is the one where the car is approaching the listener, and this is the one where the car is moving away from the listener. So if you check here, when the car is moving towards the listener, it becomes loud. The frequency becomes very high. But as it moves away, then it starts becoming a lot less. Okay. I hope that that makes sense to you guys. And if it doesn't, you guys can send me a chat and we can discuss it. Okay. So on number 3, it says a truck approaches you at an unknown speed. The sound of the truck's engine has a frequency of the sound of the truck's engine has a frequency of 210 hertz. So the truck's engine in this case is our source. However, you hear the frequency of 220. The speed of sound is 340. Remember, guys, this is a standard one. It will always be 340 unless there's a change in temperature that requires us to have a different speed of sound. Okay. So they say here, calculate the speed of the truck. We will be able to, because we've got the frequency of the listener. This is the frequency of the listener, which is usually what we want. The FL is going to be 220. The frequency of the source is going to be 210. And the V, this one, is going to be 340. 340. So this VS is what we are looking for. Okay. We are looking for the VS. Okay. So the observer is stationary. So VL is equals to 0. Therefore, this is what we're going to do. We're going to be cross multiplying and manipulating our original formula. So which means that we can take this and multiply it here and take this and multiply it there and just do some swaps and change, but you'll see it better here where it's visible. Okay. So first, you're going to take these two divided amongst each other because we've got values for this one, but we're looking for this lovey over here, right? So we're going to times these two on this side, which is going to be 1 plus Vs over V equals to Fs over Fl. And from there, we're going to take, basically, we're going to swap these two, right? We're going to say, because we want this to be, we're looking for this. So we need to move everything to the other side. So here it's going to be Fs over Fl. Then this is going to be minus 1. But if you divide it by minus to change the sign for this, it's going to be 1 minus Fs over Fl, right? And then we take this and we multiply it on this side. So now we've got our Vs, and this will be our formula now to calculate the Vs. Okay. So let's see what they say on number B. They say, how will the sound change as the truck passes you? Explain this phenomenon in terms of the wavelength and frequency of the sound. How will the sound change as the truck passes you? We know that the wavelengths are going to become much longer, which means that the frequency is becoming much lesser. Okay, but let's get it on a good one. It says here, as the truck goes by, the frequency goes from higher to lower, right? And the wavelength of the sound goes from shorter to longer. Like I've just explained, your wavelength becomes long and your frequency becomes low. Okay, so we know that your sound is high when your wavelengths are shorter or closer to each other, and that's when your frequency becomes very high. Okay, so okay, so these are our answers right there. So now we move on. So it says here, a police car is driving towards a fleeing suspect at V over 35 meters per second. Okay, so where V is the speed of sound. Frequency of the police car siren is 400 hertz. The suspect is running away at V over 68. Okay, what frequency does the suspect hear? Okay, so we know the police car has been, guys. So that's why they used an example of a police car. So the police car is forever making sound. So it's fleeing towards a fleeing suspect. So in this case, both the source and the observer or listener are moving, right? Because the suspect is running and the police car is also driving fast. So they both have velocities in this case. So here we will not have a zero value for any velocity because they are both on the move, right? So where the v is the speed of sound. So they say the source is moving towards the listener. So we need to put, for example, and a listener is moving away from the source. So we need to use this formula, right? So it's going to be FL is equals to V minus VL and V minus VS. Why do we have it like this, guys? Because it says here, remember from our little graph that, I mean, our little table that shows the um, conditions for each. It says when a source is moving towards a listener, your VS becomes a minus. Okay, so that's where we get the minus VS. And it says the listener, when the listener is moving away from the source, it becomes a minus. Remember, when the listener is moving towards the source, it's positive, but when it's moving away from the source, it's negative. But when it's moving away from the source, then it becomes a positive. So this is the question that we have. Okay. It always depends on the type of question that we given and the conditions that are stated on that condition. So you always make sure that you break down your questions to make sure you understand every condition that applies. Okay. So we are given VL and we are given VS. So now we need to substitute them into the formula. Okay. We substitute them into the formula. And this is what we get. We're going to have our FL and our FS. Our FS, we do have a value, but now we just want to deal with the stuff that's happening in the bracket. According to Podmas, that's what we do. We first sort out the bracket and then we go outside the bracket. Okay. So it's going to be, we're going to make and up on the top, on the top part, on the lowest common minus 60. So we're going to have V minus V over 6 is going to go down. This 35 will go up and this 68 will go down. So we're going to have 67 because this one here is going to be 68 minus 1 because they've got the same, the common elements. They both have V. So it's going to be 67 over 68. Okay. When we get to this part here, it's going to be 60 V over 68, right? And this one is going to be 34V over 35. Okay, these ones factoring it out, we can, so you're going to have this big bracket. I hope you're all using your scientific calculators so you can be able to calculate these one, two, three brackets, okay? And you times that by 400, and this is what it will give you, 405.7 hertz, okay? So that is our answer. So that is the frequency that the listener will observe. It's quite a long question, but it was, at least it was very dense for you guys to be able to understand. So on number 5, it says, explain how the Doppler effect is used to determine the direction of flow of blood in the veins. Ooh, this one is very interesting. This, remember, is what we spoke about with the sonograms, etc. So they say an instrument called the Doppler flow meter can be used to transmit ultrasonic waves into a person's body. Okay. I just wish I could get I just wanna, okay. I just wanna show you guys. I just wanna show you guys how how it looks like, right? A Doppler flow meter. Let me just go to a Doppler flow meter. I wanna show you guys how it looks like. Just a few seconds. So it's much easier to understand if you actually see the mechanism and how it is used. Okay, okay, I got it. Let me just try and share this with you. Okay, so you see how it looks like. So basically, this is how a Doppler flow meter looks like. It's going to be the sensor over there, all the bubbles and sound, and this is how the frequency is transmitted. So this would be your little vein that's carrying your blood inside. Okay, so this is what it means when they talk about a Doppler flow meter. Okay, now let's go back to what we were doing, what I was trying to explain. Okay, so it says here, an instrument called a Doppler flow meter can be used to transmit ultrasonic waves into a person's body, like I just showed you guys right now. So this is your, this is your Doppler effect, and this is the waves that are transmitted inside your body. So what happens there is that if you transmit into a person's body, the sound waves will be reflected by tissue, bone, and blood, etc., and measured by the flow meter. So if blood flow is being measured in an artery, for example, the moving blood cells will reflect the transmitted wave, and due to the movement of the cells, the reflected sound waves will be Doppler shifted into a high frequency if the blood is moving towards the flow meter, and to a lower frequency if the blood is moving away from the flow meter. So you see, so basically your flow meter in this case becomes your it becomes your source, right? So it becomes your source. So that's why they mentioned that it calculates the different in frequencies of your blood flow. Okay. So if there's no blood moving, that means that there will be no frequency transmission, right? So which means that maybe there's a blood clot. So that's how scary it gets when it comes to the abnormalities that can occur from such a thing. Okay. So now let's move on. We're almost done, and it's almost time to discuss the by the person. Assume the speed person in a car traveling at 22. Okay. So what does that mean, guys? It says here, it means that this time around, the listener or the observer is the one that is moving, and the source emitted sound waves at what frequency. The source in this case is standing still. So which means that you're a person, you are traveling, and you're approaching a sound of source, okay, at 410 hertz. What is the frequency of the sound of what is the frequency of sound waves observed by the person? Assume that the speed of sound is 24. So here, that's why we do not have the speed of the source, because the source is stationary and the listener is the one that's moving. So that's why we have a formula like this. But because the car is approaching the source, which means it's moving towards the source, it becomes a positive. When the listener is approaching the source, it becomes positive. But if it were moving away from the source, it would be a negative velocity. Okay. So there we are. So the source is stationary, so Vs is 0. And rearranging the formula, this is what we're going to have, right? We didn't even rearrange it, still the same. It's just that we minus the source, and here it's a positive. So we put in everything that we have, which is the 340, the 22.2, which is the speed of the person in the car, okay? And the 340 there, and the 410 is the frequency of the sound of the source. And this will give us 436.8 hertz, okay? So guys, we've reached the end of our problems. I hope that everybody had a good lesson, and you now understand everything that is happening with regards to the source, the listener, the relativity between the two, when one is moving away, when the one is moving to, that is all part of the Doppler effect that we have been doing. Okay, so thank you guys so much for a beautiful lesson, and that is the end of our problems. But I think next week we're going to start again with some more problems. Okay, I don't know. I'm thinking that maybe because we've already started with the Doppler effect, we can continue with the revision for Doppler effect questions, and then from there we move to work, energy, and power. Okay, because I want us to start our assessment soon. Our assessment in this case, it's going to be us revising papers. Okay, we're going to be doing some revision on term 1, term 2, and term 3 work, and we're going to be trying to um, see and testing how much you guys have learned and how much you guys can do. As you know, guys, your prelims are coming pretty soon, so you guys need to be prepared, and that's why I am here, to make sure that everybody is prepared. So let's work together, and next week let's do some more revision questions, and soon we're going to be starting with question papers, and we're going to have our assessments soon. Okay, but I will let you guys know everything on Monday when we meet up. But for today's lesson, that is the end. I hope that you guys are knowledgeable and you are happy. Thank you guys so much and goodbye. Reminding you can get me on LinkedIn or on my email c3dt@gmail.com if you have any further questions with regards to the problems and things that you don't understand, things where you are stuck. Guys, this is my trick. This is a do or die. You have to make sure that you get every understanding in your right place, in your mindset. Okay. Thank you guys so much and goodbye.